Hello and a very warm welcome to the first session of the third round of the DAAD Climate Lecture Series, organized by the German Academic Exchange Service DAAD and the Global Centres for Climate and Environment. My name is Hannah Cornelius. I'm the Program Manager of the DAAD Global Centres program, and on behalf of the DAAD, I would like to welcome you all, and I'm delighted that all of us have gathered here today to listen to you, dear Professor Kala. The DAAD is funding a total of 4 centers for climate and environment with support from the German Federal Foreign Office. And all of the centers deserve their title insofar as they are based in minimum 2 countries of the Global South and Germany. If you would like to find out more on the program, you find a link to the program's website in the chat. And before giving the floor to today's chairs of the session, which will in the beginning be Professor Edeltraud Günther from UNU Flores and afterwards Dr. Danish from IIT Madras, both from the Global Centres for Climate and Environment ABCD. And they will introduce then our guest speaker. I would like to provide you with a few organizational notes and conduct a short survey with you to get a better impression of the audience here today. So first to the technical details, your microphones and cameras are switched off and will remain so for the entire event. Questions can be asked at any time via the chat. We will collect all questions and pose them to Professor Kala after the lecture in the Q&A session. We are recording the event and publish it on the DAAD channel on YouTube and on our website. So now we would like to conduct the survey with you. We have prepared 2 short questions and kindly ask you to participate. So first, we would like to know from which world region you joined today. So hope everyone sees the question. And so you could just indicate if you're joining us from Sub-Saharan Africa, North Africa and the Middle East, Asia, Latin America, Europe, North America, Australia. So let's see who's with us today. So until now, we have representatives from North Africa and the Middle East, Asia, and Europe. And Sub-Saharan Africa. I will give you a bit more chance to find everything. So let's come to the second question. And there we would like to know why you got here. So are you part of one of our 4 climate centers, from student to senior scientists? Or are you researching in the field of climate, but not within the climate centers? Do you have a particular interest in Professor Kala's work and the topic of today? Or are you generally interested in climate change or in DAAD events in general?
And multiple options are not possible, what I just saw, because I'm very much interested in your presentation, Kala, and but I can also be so.
I think that's, of course, valid for all of us. But yes, as long as you belong to the centers, then this would be the first option to answer there. Okay. Yeah, but there already are participants with us that are especially interested in Professor Kala's work, unless they're not part of our centers. So this is great that we reached out to those as well. Okay, so thank you for this short impression and the insight. And I now hand over to Professor Edeltraud Günther, who will moderate now the lecture and present us the speaker of today. So Edel, the floor is yours.
Thank you so much, Hannah. And I'm so happy that I can introduce Kala to you. We met before, so therefore there's also a personal connection. And the other connection is that Kala's work is really also related very much to what we are doing here at United Nations University. He has a PhD and Master of Science in Environmental Engineering. So I think this is just the optimal topic for such a presentation here. And you are also a chartered engineer and a fellow of the Institution of Civil Engineers. And what impressed me very much is that you are an internationally recognized water resource management expert. So that means you are really a scientist and have all this experience of science with a specific focus on urban water issues. But you also have the international practical experience. And that's what I also understood when we initiated the ABCD Center, that it's really about the combination of research and practice. So if you are interested more in Kala's research, read his articles. If you're more interested in practice, then also look at reports that he co-authors, look at also advices he gives. And my feeling is that exactly this combination of research and practice is the benefit that we can also get here in this DAAD lecture series. And therefore, I'm very much interested also in listening to you, and explicitly also said, yes, I am very happy to introduce you. We will now listen to your 30 to 40 minutes presentation, and then we have the option for questions. I understood that the lecture will be recorded. So if you have someone who could not make it today, but who is interested, they can also watch it later. I think that's really a very good idea also for multiplication and also to use taxpayers' money wisely. And for us, for example, as professors, we always like to use those recorded lectures also as materials for our lectures. So I'm now very much interested in your lecture. Hand over to you. And then after the lecture, Danish from IIT Madras will be moderating the Q&A session. Thank you for coming. Thank you for joining. And thank you to DAAD for organizing this lecture series. I'm very much interested in the next hour. And over to you, Kala.
Thank you very much. Can you all hear me okay? Okay, so I'll just share my screen, and I just want to make sure that you can all see my screen as well. Can you see the screen okay? Okay, I can't see anyone anymore, but
I think we can all switch off our cameras, Hannah, or how shall we proceed? Yeah, okay, that is also for the recording will be better.
Idel, can you see my screen okay?
Yes, perfect.
Okay.
It's perfect.
Perfect. So thank you very much for the kind introduction, Idel, and it really is an honor for me to give a DAAD Climate Lecture today. Just to give you some context, I come from the IWA, and our focus is mainly around urban water issues. And so the focus of my presentation predominantly will be around some of the urban water issues. To start with, I think it's very important for us to recognize that water touches everything. According to the FAO, that's the Food and Agriculture Organization, 70% of all fresh water is used in agriculture. And now with climate change, rainfall is less predictable, and so food systems will become more fragile. When we think about energy, according to the World Bank, nearly 90% of electricity is water dependent. And climate change means water stress, and so without reliable water, there is a risk that we will lose power security. And when we think about urban, it's predicted that by 2050, 2.5 billion more people will live in cities, mainly in the developing world. And it's not just that these populations are growing. The populations are also growing up. Their living standards are improving. And so the rate at which they're using water is also increasing. So on the one hand, you have the numbers increasing, you have the amount of water that they're using, most likely to increase. But on the other hand, climate change means that the water availability might be under stress. And so the demand deficit is likely to get worse. Now, when we think about health, the WHO quotes that 80% of diseases in developing countries are still linked to poor water supply and sanitation, and this will only get worse with climate change. Now, all of this isn't just data, it's really the foundation of why water touches everything and why water must be at the heart of all climate conversations. So if we take mitigation to start with, now that presents quite a complicated and evolving challenge for the water sector. At the higher end of estimates that you'll hear from various reports, they say that the urban water sector contributes around 10% of all global greenhouse gas emissions. And within this equation, wastewater is really the key challenge. Because you see, drinking water, with drinking water systems, most of the emissions are what we call Scope 2 emissions, and they're related to the electricity that we take from the grid. But with wastewater systems, we're generating quite a lot of Scope 1 emissions because of the actual processes that we employ in our treatment plants. And so the Scope 1 emissions tend to dominate. And this distinction is quite important because when we look at future mitigation strategies, they'll be different for drinking water systems and they'll be different for wastewater systems. And where this becomes quite complicated is implementing low carbon solutions isn't cheap. It often requires major capital upgrades, and sometimes it results in much more complex operations, particularly in the early stages of deployment. And what makes the situation even more difficult for our sector is our ability to, predict our emissions accurately is also not very good. And so when we're looking at implementing low carbon solutions, we don't really have very good data around what the impacts of that might be in relation to the emissions. Now, when you throw into the mix the political uncertainty that we're seeing now, where many governments, due to economic pressures, to energy security concerns, and in many cases even social pushback, people are a bit uncomfortable about some of these narratives that are appearing. And so what we're seeing is that we're seeing governments actually softening or delaying their net zero ambitions. So that's created another level of uncertainty. And so what you have in our sector is water utility leaders in a difficult position, right? On the one hand, they're being asked to make long-term infrastructure decisions. We have to make decisions today that last for 30 to 50 years in the water sector. But they're having to make those decisions in an environment where both the science and the politics are quite uncertain. But to conclude, mitigation is essential, right? But the pathway forward for us in our sector requires us to be more flexible. We have to have a much more sort of systems thinking approach to what we're doing. And we have to learn how to make smart decisions under uncertainty. Now, as I said, nowhere is the uncertainty more visible than in wastewater emissions. In wastewater, as we start to decarbonize our grid electricity, what we call our Scope 2 emissions, we're starting to see our process emissions, our Scope 1 emissions really starting to dominate. And here what you can see on the diagram is sort of a traditional flow diagram of a wastewater treatment plant. But you see, the problem is that we don't fully understand our Scope 1 emissions well. And the current baseline assessments that we use are really based on very limited science. One of the challenges we have is understanding what we call fugitive emissions, or leaking emissions, if you like. And this is things like methane and nitrous oxides. And they leak from various parts of our treatment processes, as you can see in the diagram. And these fugitive emissions, they tend to be the most potent emissions, right? Methane is 25 times more potent than carbon dioxide, and nitrous oxides are almost 300 times more potent than carbon dioxide. And this is important to note because any small changes in the processes that we use in wastewater treatment can have potentially disproportionately large impacts on greenhouse gas emissions. Now, most water utilities, they currently estimate their greenhouse gas emissions using emission factors developed by the IPCC. But many researchers and practitioners believe that these IPCC emission factors underestimate the actual emissions that come from wastewater systems, particularly the fugitive emissions. You know, things that leak from sewers and from various parts of the treatment, and also in sludge handling. Now, when you look at this graph that I'm showing you here, this chart, it shows real measurements of nitrous oxide from around 51 wastewater treatment plants. And what you see on the x-axis are different treatment process trains, right? So A/O is a certain type of treatment train, anoxic, oxic. It's not important to know what they are, but they are all different treatment trains. That's what the x-axis is showing. Now, the box and whisker plots actually shows the range of emissions that you find from plants that have the same treatment trains. So you have, I don't know, 6 or 7 different treatment trains, and you can see the variation in nitrous oxide emissions. Now, at first, we might expect that similar treatment trains produce similar emission factors. But what this result shows us is something much more complex. Even among plants that use the same treatment processes, emissions can vary quite enormously, often by several orders of magnitude. And what this tells us is that emissions are influenced not only by the treatment technology that we use, but also by a lot of the site-specific conditions, the operational conditions that we have at a particular site, the environmental and the climate conditions that we see at different sites. Now, all this creates a major challenge for our sector in terms of mitigation, because if the emissions vary so much between similar systems, then how can we start to produce reliable carbon audits? How do we compare technologies fairly? And how do we make sensible investment decisions about mitigation strategies? Now, here on the right, you also see a similar graph for methane emissions, where the variation is also of several orders of magnitude. So this is where our sector needs better science. We need better monitoring, we need better data, we need better models, and ultimately we need better ways of understanding how real systems behave under real operating conditions. Because you see, without that understanding, it becomes very difficult for us to make confident and cost-effective mitigation decisions. So I've talked about, wastewater process emissions and how they're important but highly uncertain, and that we're struggling to estimate them. But at the same time, our sector is really seeing wastewater as a major opportunity. And in IWA, we often say that the next 20 years is really going to be the golden age for wastewater and sanitation, particularly in the global south, in developing countries. Because you see, many of these countries, these developing countries, they are just now embarking on their wastewater infrastructure journey. And what that means is that they're not locked into the sort of historical mistakes that we made in the developed world, in the global north. You see, in many ways, the last 70 years in the global north was like one big pilot study. They started with very large, clunky, energy-intensive systems, and gradually they improved them incrementally through innovation, through operational experience, and better scientific understanding. So today we're seeing the emergence and the convergence of more efficient and more elegant solutions to wastewater treatment. Technologies like you see on the screen here, aerobic granular sludge, Anamox, thermal hydrolysis, these all change the physics of the processes, and they allow us to achieve the same treatment outcomes with smaller footprints, with lower energy demand and lower operational costs. And so for developing countries, this creates a huge opportunity as they start their wastewater journey, because they really do have this opportunity to leapfrog, right, to implement from the outset more efficient, more resource-oriented, and potentially lower carbon wastewater systems. And we're seeing countries like China, India, and countries in sub-Saharan Africa already embracing these types of technologies. And they see opportunities to build much more elegant wastewater treatment works. So while in the past, wastewater treatment was viewed as a high energy intensive and high carbon sector, now we see a real opportunity for us to become part of the low carbon economy, and also become an exemplar in that respect. However, as we innovate and intensify wastewater systems, we also need to remain cautious. Because you see, one of the great paradoxes of mitigation is this: reducing energy use does not always mean reducing greenhouse gas emissions. For example, some innovations, and I showed you some just in the previous slide, say, for example, in the process of nitrification and denitrification of wastewater, there are lots of innovations that deal with this, which are now using much less energy. But as a result, there are some unintended consequences. Some of these energy-efficient processes are actually increasing the emission of nitrous oxides. And as I said, that's a greenhouse gas that's 300 times more potent than carbon dioxide. So in other words, what looks like efficiency in terms of energy and electricity may actually not be efficient in terms of climate impact. So when we talk about low carbon or net zero, our focus has always got to be around the total greenhouse gases, not just electricity or kilowatt hours. And what this does now is it's creating a lot of interesting possibilities. You see, as electricity grids become increasingly renewable, the relationship between energy use and emissions may fundamentally change. And in some cases, and I know this might sound counterintuitive, right? In some cases, using more electricity, provided it comes from renewables, may actually help us reduce the overall greenhouse gas footprint of our system. Now, what we're seeing in our sector is that this type of thinking is sort of potentially could fundamentally reshape the logic of wastewater treatment design in the future. And we are seeing this in IWA. We're seeing the emergence of technologies which are around electrochemical processes. And these tend to be more precise in dealing with contaminants, and they produce less fugitive emissions. But they do need more electricity. But if that electricity is coming from renewables, then it's okay. So the message is simple. As we innovate, we need to better understand the full greenhouse gas footprint of our choices, not just the energy and the electricity savings. Now, I think there's a deeper lesson in all of this for us, right? Climate change is not simply adding new constraints to urban water systems. It's actually destabilizing many of the assumptions that those systems were originally designed around. The future is becoming much harder to predict because of climate change. And as I said earlier, utilities under that uncertainty are still being expected to make decisions today that shape our cities for 30 to 50 years from now. What this means is the challenge is no longer about optimization, right? It's learning how to operate under uncertainty. And this is what uncertainty increasingly feels like for urban water utility leaders. The complexity keeps increasing, while the clarity we need to make confident decisions is not there. You see, in the past, resilience meant strength. Build it strong, weather the storm, and then rebuild. But in this fog, strength alone isn't enough, because we're no longer simply surviving shocks. We're operating continuously in conditions of uncertainty. What we need now is intelligence, systems that can sense, that can learn, and can adapt as they go forward. When you look at this image, right, the headlights are cutting through the mist. We can't see the whole road ahead of us, but we can see just far enough to keep moving. And we can learn from what we encounter along the way. And so we can adapt as we go forward. And that's the key. In uncertainty, progress doesn't come from resisting pressure. It comes from learning through it. Every disruption, every drought, every flood or contamination event becomes a calibration for the next challenge. And that brings us to perhaps the central challenge for urban water systems in the climate era. How do we design our infrastructure for a future that we cannot fully predict? Now, I want to share something with you. It's something about the idea of riding through the fog. And this is sort of very much an illustrative example, so don't read too much into the data. Now, in the past, when uncertainty was lower, we designed towards a single point in the future, a fixed dot on the wall. We assumed the pathway there was stable, so we built systems with very little flexibility and very little room to adapt. But as I said, with global change, the future is uncertain. Different emission scenarios, different models, different urban growth rates. The only certainty that we have is that the future is highly uncertain. Instead of one destination, we now face an envelope of possible futures. This shaded band sort of tries to represent an uncertainty envelope over time. So the question is, how do we design within that envelope? We do this by building in smaller, deliberate steps, creating systems that can evolve incrementally. And at the end of each step, we leave ourselves an opportunity to pivot in different directions, so we can take different paths depending on what we've learned along the way. So we have this ability to span the uncertainty envelope. And this is what the fog metaphor really means. We can't see the whole road ahead of us, but we can illuminate the next few meters. We can move forward in small steps and then adjust. Each step gives us new information, helping us to recalibrate the next one. And this is how resilience evolves, not through rigidity, but through learning in motion. And I'll try and give you some examples of this later in my talk. So if we accept that the future is uncertain, that rainfall, water demand, urban growth may all evolve in unpredictable ways, then adaptation cannot simply be about building bigger water supply systems. It must also be about using the water we already have more intelligently. And for me, one of the most important aspects of climate adaptation is an understanding of the productive use of water. What is it we want the water to do for us? And how can we match the quantity and the quality of water for that intended use? And what this means is that we move away from this idea that we need high-quality drinking water for everything. Of course, we need high-quality water for drinking, but for flushing our toilets, for gardening, we can use waters of different grades. And when we do this, something powerful happens. We begin to reuse water again and again and again, multiple times, often in a cascading way. And when we do this, we maximize the productivity of water by doing more with less. Now, for me, the real opportunity in this thinking is to apply it to the entire urban water cycle, from the moment that water enters the city to the point at which it leaves. And this is where integrated urban water management begins. Now, for me, integrated urban water management is simply this. It's looking at the entire water cycle through a single lens. So we look at our drinking water system, our wastewater or used water system, and our stormwater system, and we look at them all collectively through this single lens. And most importantly, we look at all the water that flows through this system as good water. It's just water of different grades or different qualities. So if I had a growing demand for drinking water or domestic water from consumers, I've got two options. One is I can import water from afar, transfer water and all the energy that might involve from a river, let's say, to meet that growing demand. Or I can invest in leakage management and demand management that frees up high quality drinking water. Now, if I want to flush my toilets or water my gardens or my parks, I can import water from a long distance and bring it to the city for that purpose, or I could invest in grey and black water and use that for that purpose. So by looking at the whole water cycle through a single lens in this way, you can start looking at how to invest in efficiencies from within your system to meet your growing demand, rather than investing in transferring water from distances to meet that growing demand. And now, critical to all of this is integrated urban water modelling, where we model flows and contaminant fluxes across the entire urban water system using mass balance techniques. And what this allows us to do is to match these different grades of water to different uses, hence allowing us to meet that growing demand by looking for efficiencies from within the system and not thinking about just importing more new water. Now, with these new tools, we can start modelling packets of water as they move through the system, with each packet having a digital signature of where the water came from, its quantity, its quality, the effort it took to treat that water and to convey it. So every drop of water becomes more than just the water alone. Every drop becomes embedded with information about energy, carbon, treatment effort, scarcity, and value. Now, some time ago, I did a project with the World Bank where we were looking at how is Nairobi going to meet its growing demand. And the decision of the decision makers was to just invest in more surface water sources, go further away and import more surface water to meet the growing demand. When we did our integrated urban water modelling, we were able to show that actually there was quite a lot of water within the system that was being lost, and that water could help meet that growing demand without building new infrastructure. So investments in leakage management, demand management, some rainwater harvesting at a cluster level, some greywater reuse, that all of this could be used effectively to meet that growing demand. And these findings were published in a book that can be downloaded. See, what Nairobi showed us, and we've applied this approach to many other cities, is that we can meet growing demand, not by finding more water, but by using what we already have more efficiently. But it raises a bigger question, right? Because once we begin to understand water systems dynamically, we can also begin realizing that adaptation is not only about efficiency, it's also about redesign. What if we didn't just optimize the systems we have, but started to design systems differently from the outset? And that's exactly what we see in places like West Basin. You see, the West Basin Initiative in Los Angeles is a great example of the productive use of water. It was developed in the 1990s to address water scarcity, and it turns wastewater into multiple grades of what you call designer waters, or waters of different flavors, tailored for uses like irrigation, for industrial cooling, for groundwater recharge. And by matching the quality of the water to its purpose, the system maximizes the productivity of water, while at the same time reducing the overall water footprint. And it uses a modular plug-and-play design that allows flexible treatment trains to deliver different quantities of these different grades of water at different times. And this is really a hallmark of smart reuse. And importantly, this gives operators options. It gives them flexibility. And in uncertain futures, optionality becomes a form of resilience. Now, the West Basin shows us what's possible when we design systems to use water more productively. But it's still one system, right? One facility. The real opportunity for us is to scale this thinking across an entire city, across multiple sources and multiple uses. And that's where cities like Singapore and Chennai come in. Now, when we scale this thinking across the city, we move from managing water as a single source to managing it as a portfolio of water sources. And this is where resilience really begins, because diversified systems can rebalance internally as conditions change. If one source fails, another can compensate. Now, Singapore and Chennai have shown what's possible by turning diversification into a core principle of water security and climate resilience. Now, I'm sure many of you know the Singapore example, the 4 national taps. And if one tap dries up, the other 3 taps can augment and provide supply. For me, the Chennai portfolio of options is more interesting, and it's their Aru Kudum's approach, or 6 pots. And this approach was developed in 2019 during the severe drought, and it involves 6 sources. Now, some of them are pretty obvious. So conservation is where leakage management, demand management is employed. You've got desalination, you've got you've got surface water and groundwater, a lot of reuse in Chennai by industry. But there are some interesting options there as well. Things like quarries, right? They had a lot of disused quarries that became natural sort of rainwater harvesting structures. And they looked at how, I mean, that water is quite contaminated. So they were looking at how they might use that water by treating it through natural systems before using it for some purpose. So both cities show the same principle in action, that diversity creates resilience and diversity reduces vulnerability. But once we begin managing water as a diverse and adaptive system, another question emerges. What kind of infrastructure is actually best suited to deal with uncertainty? Because traditional centralized systems are designed for stability and predictability. But uncertain futures may require infrastructure that is faster, more flexible, and capable of evolving over time. So what we're seeing at IWA is really big interest in decentralization. And we're seeing this as a tactical opportunity, an ability to be agile. In uncertain environments, agility itself becomes a form of resilience. You see, traditional centralized systems are cumbersome and heavy. They require a lot of effort to get them moving. Lots of planning, lots of land approvals, lots of money, lots of time to implement. And all of this leads to delays and procrastination. By the time many centralized systems are finally delivered, the conditions they were designed for may have already changed. Now, in contrast, decentralized or distributed systems have a certain agility. They can be rolled out in stages and at a much faster pace. And right now, within IWA, we're seeing some really interesting and creative work happening in this space. Now, imagine, most cities, you'll have a centralized core where you have a centralized system, water system. And as the city grows, our natural instinct is to grow that centralized system. But what if, instead of extending our centralized system, we took a different path? What if we ring-fenced our existing centralized core and surrounded it with distributed modules? And these distributed modules would have lots of advantages. First, they allow incremental growth, so we can expand our system in stages, delivering immediate benefits to communities along the way. They also allow us to follow urban growth patterns more effectively, rather than relying on predictions. In other words, these systems evolve with the city, rather than trying to predict the city decades in advance. And they also allow phased investments, so we can stage our investments thoughtfully and strategically. Importantly, these systems also give us technological flexibility. They enable us to be agnostic about the technologies we're using, tailoring solutions to different needs. For example, solutions for low-income communities can differ from those for high-income areas, but the end goal would always remain the same: safe, equitable, and inclusive water and sanitation services for everyone. In terms of climate change, being technologically agnostic is important because in uncertain futures, locking ourselves into one technological pathway can itself become a vulnerability. Now, these systems also support the circular economy objectives better by generating resources close to where they are needed, minimizing the transport of water. Water is very heavy, so if you move it long distances and then try and move it back, it's very energy intensive. So here you're using those sources very close to where they're being generated. Another strong feature of distributed systems is that they are inherently more resilient to climate events. You see, when an extreme event occurs, like say flooding, the failure can be contained within a single module, and we can avoid that failure propagating throughout the entire system. And this is what tends to happen with centralized systems. You know, one extreme event knocks out the entire centralized system. And this is really important in terms of climate futures, right? Because shocks are becoming more frequent, more intense, and less predictable. So distributed systems are not simply smaller systems. They are systems designed around adaptability, circularity, containment, and optionality, all reinforcing each other at the same time. If you remember earlier, I showed you this uncertainty envelope. Distributed systems really allow us to build in stages and learn along the way, and then pivot as we go along the way. So they do allow us to span this uncertainty envelope. Now, around the world, cities are already demonstrating what adaptive circular decentralized systems can look like. And you can see some of the examples here. If you take Oceansharm, for example, in Sweden, they've reduced their water footprint by 50% through closed-loop thinking. Their black water and their food waste are co-digested to produce fuel for local buses, while their grey water is used to generate struvite, which is a fertilizer, phosphorus-based fertilizer. And their treated sludge is also repurposed as a soil conditioner. So they're sort of taking everything in their system and trying to reuse it multiple times. Now, these are not experiments, right? They are real-life examples of how well-managed water systems can build resilience, flexibility, adaptability, and circularity all at once. And perhaps this is why nature-based solutions are attracting so much attention in climate adaptation. Because the very qualities we're searching in our grey infrastructure, resilience, flexibility, adaptability, they are qualities that natural systems already possess. You see, unlike rigid engineering systems, natural systems are dynamic. They evolve, they regenerate, and they can adapt to conditions of change. Now, they're already widely used in water management, from source water protection to urban drainage to flood control, and even to wastewater treatment and reuse. Now, in this slide, you can see a nature-based sort of setup for closing the water loop. Now, the public love these systems, right? Because people generally prefer green spaces over concrete. But for engineers, they do present challenges. Their performance can vary across seasons and environmental conditions. There is still very limited standardized guidance for the design and performance assessment of these systems. And their benefits, like biodiversity, cooling, and recreation, which are all really powerful benefits, they're quite hard to monetize. So it affects our ability to articulate their cost benefits. And that raises an important challenge. Our engineering and economic frameworks that we currently use are still better at valuing rigid grey infrastructure rather than adaptive green infrastructure. But this is beginning to change. The science is maturing, the design tools are improving. And as climate pressures intensify, the value of adaptive, regenerative, nature-based systems are going to become impossible to ignore. But for me, one of the real potentials in nature-based solutions lies in how we design them, not as fixed installations, but as modular systems that can evolve over time. Now, here on this slide, you can see some of the building blocks of sustainable urban drainage systems. Green roofs, pervious pavements, infiltration trenches, etc. Now, each of these can operate effectively on their own. But the real value comes when they're connected, forming a distributed network that collectively manages stormwater, filters pollutants, and recharges groundwater. Now, these modular systems are being embraced all across the world, and they have different names and different design philosophies. In China, they're called sort of sponge cities. In the US, low-impact development. In Europe, we tend to use the term blue-green infrastructure. I mean, basically different names with the same idea, right? Harnessing natural processes in a modular way to make cities more resilient, adaptable, and livable. And because these systems are modular, they can evolve incrementally as uncertainty unfolds, allowing cities to learn, adapt, and recalibrate over time. Now, if you imagine that the urban drainage options that I just showed you on the earlier slide are, if you like, a briefcase of options represented by these colored dots. Now, at each stage of urbanization, we can open up the briefcase and select the right combination of modules to fit local conditions, like rainfall, topography, and growth patterns. Now, as the city starts to evolve and rainfall trends change, we can adapt again and again, reconfiguring those modules, branching in new directions rather than being locked into one fixed trajectory. Now, remember the uncertainty envelope I showed you earlier. This approach really allows us to design within an envelope of uncertainty, building in stages, testing at each step, and always leaving ourselves multiple paths forward. That's the beauty of modularity, that it keeps our options open. And the data reinforces this point, right? These modeling studies show that modular nature-based systems consistently outperform traditional centralized drainage systems over a wide range of performance measures. But importantly, they also perform quite well under various rainfall scenarios, not because they eliminate uncertainty, but because they are designed to operate within uncertainty. They can absorb shocks, reroute flows, and keep functioning, even as climate and cities around them change. And perhaps that is the deeper shift climate change is forcing upon us. Moving from systems optimized for stability towards systems capable of evolving under uncertainty. And perhaps this leads me to one final idea. For decades, our infrastructure philosophy has focused on resilience. Build systems strong enough to absorb shocks, recover, and bounce back. But in a world of accelerating uncertainty, perhaps resilience alone is no longer enough. This is kintsugi, the Japanese art of golden repair. When a ceramic piece breaks, its cracks are filled with gold, transforming damage into design. The object actually becomes more beautiful, not despite its fracture, but because of it. In many ways, this captures the idea of anti-fragility. Systems that do not simply survive disturbance, but learn, adapt, and improve through it. And perhaps this is exactly what modular systems, distributed infrastructure, diverse portfolios, and adaptive designs begin to offer us. Not infrastructure that simply resists uncertainty, but infrastructure capable of evolving through uncertainty. Because the cities that succeed in the climate era may not be those that resist disruption most aggressively, but those that learn from disruption most intelligently. Now, I always finish with this slide, and it's just to say that, the water sector no longer has the option to stay in the business as usual lane. Global change pressures means that, our 19th century infrastructure cannot cope. Now, most of the water sector is in the middle lane. They're trying to tinker with their existing systems, and they're trying to sort of modify what they already have and do things retrospectively. But I think the true opportunity is in the developing world, in the global south, where they're just embarking on journeys, right? And they have this opportunity to reimagine how they view water in the face of climate change and all these other uncertainties that they face. And they can really reimagine a new paradigm where we rethink the way we use water, the way we reuse water, and the sort of actual the typology of the designs that we implement. So I think the future is quite optimistic, particularly in the global south. Okay, that concludes my presentation. Thank you very much.
Thank you, Professor Ramana, for your thought-provoking and very insightful presentations on how the status quo of water crisis is there and how you have a balanced distribution of greenhouse gases and the energy and the type of technology and the methodology that needs to be used, and connecting it to the adaptation strategies that needs to be adopted across different treatment and utilization and distribution techniques It's very, very thought-provoking. So now we will be opening the sessions to the Q&A. So I like to hear from the participants and attendees to have your queries in the chat box so that we may hear from Professor Kala. Any questions from the attendees? Please put it in the chat box. Yeah. So there is one question from one of the attendees. So what are the main obstacles when moving from centralized system to decentralized one?
Yeah,
So
so there are there's two thinkings around this. One is around in the global south, where we historically have had, a centralized core. And so the question is, when we are expanding our system, this ability to not expand a centralized system, but to actually build modules around it. And that's not too difficult to do because it's actually a new system. But where you have heavily centralized systems, when you want to try and morph them into a more decentralized approach, it's a little bit more tricky because you have to start to decommission certain elements of your existing infrastructure. Now, some time ago, when I was an academic, a little bit way away, we used what we call morphing algorithms, right? And actually, they used a very similar principle to what you see in the Michael Jackson video, Black or White, where you see these faces morphing from one image to another. And what we did was we developed an optimization approach where we designed our decentralized system from scratch, right? Assuming that there was no system in place. And then what we did was we looked at our existing system and we systematically tried to identify which elements of our existing system still feature in this sort of ideal optimized decentralized system. And we would then take those elements and put them into the system, right? So therefore we wouldn't have to rebuild those components. And then we would look at those elements that didn't appear in the decentralized system, and then look at what would be the cost of including them in terms of their impacts on the benefits. And so what we found was that a certain proportion of those elements could still be incorporated into the decentralized system, but that we would ultimately have to decommission large parts or a certain portion of our system. Now, this becomes problematic, right? Because decision makers generally don't like to decommission things. So it is hard, but there are approaches and algorithms that allow you to systematically look at that transition process over a period of time, 5 to 10 years, that any future investments are really contributing to moving you towards a decentralized approach, and that you systematically decommission certain elements that inhibit the move in that direction.
Yes, in continuation to that, there is a question. So while for the distribution system, there are sources, generally reservoirs, which are fixed, and how the vision of decentralized system in this water system is like distribution system works, or can there be any other alternative such as like a new source of groundwater or desalination water? So how do you think that works?
So when you look at these approaches, it's very context specific, and we looked at the deployment of decentralized systems in sort of several towns in Uganda. And, where we had, say, a water body, a river running through, then how we located the different modules would be very much related to the location of those water bodies. Where we had groundwater, then that could augment water within those decentralized units. But it's very context specific, right? It's not to say that decentralization works all the time. You have to really look at the population densities, the topography, and where your major water sources are. And then through modeling, you're able to identify if moving into a more decentralized approach is in the long-term benefit of you, both in terms of moving water, but then the opportunity to reuse. Now, generally what we've done in the past is when we wanted to reuse water, right? We move water into a city, then we move it long distances out of the city, treat that wastewater, and then move it back into the city. And as I said, water is quite heavy and it's a lot of energy involved. So even that process of treating water for reuse, if you just even do that step inside your decentralized unit, either at a cluster level or at a housing estate level, then it's going to make a lot of sense. And we're seeing a lot of that happening.
Okay. So, from your experience, so how do you take away the integrated local and traditional knowledge and the new technologies that are emerging into the resilience planning, and much more of like adapting into the nature-based solutions, as we've been like also saying blue, green, gray infrastructures. So how that works?
I think the important thing for people, particularly for utilities, right, is to not be religious about any approach, right? What we find when I mix with utility leaders is that they tend to be quite religious about, centralized systems. They're the only ones that work, or, they are moving very fast into nature-based solutions. I think what you need to have is an open mind. And you need to understand that there are all these different approaches that exist, and there are limitations with these approaches, and there are potential benefits. And then through a deep analysis of your own local context, right, you pick what is suitable for you. And I see the emergence, and that's why I think technology agnosticism is important, because I see the future as being one where we, different strokes for different folks, or different horses for different courses, whatever phrase you want to use, but where you're really tailoring the solutions to meet your own local needs. And you have the confidence to have different solutions in different locations. Now you see that, for example, in the electricity sector with solar panels, right? You have different types of solar technologies being offered to wealthy people, different types of solar technologies which are more cost effective for people who can't afford so much. Whereas with our sector, we believe in one size fits all. And I think what we need to try and do is to try and embrace the fact that, there are different solutions, and that governments or utilities cannot have a monopoly on the types of solutions that people should have. So I think it's having an open mind. It's recognizing that there are lots of hybrid solutions, and then understanding your local context and having an honest analysis of what would best suit your local context.
Okay. So on many forums, the adaptation discussion focuses on policy ambitions, and when the infrastructure has been in the vulnerable regions, especially on global south. How do you characterize it for a climate resilient, or as you said, that it needs to be a modular system? How do you characterize it? Because most of the discussions may have a political agenda.
Yeah, I think that is probably the biggest challenge, right? It's the political agenda. And I think that what we have to do is we have to learn from other sectors, right? And when you learn from other sectors, if you deregulate a little bit, I mean, water is very important, right? It has a big health implication. So it has to be protected. It has to be regulated. But I think the government's role is to set the guidelines on what the expectations are, what should be the outcomes. But then they should allow different actors to come in to try and deliver services. Now, if you take, for example, mobile phones, I know this is an analogy I use a lot, but, I travel a lot around the world, and sometimes I travel to very difficult environments. And so I'll go to a place where people are still defecating in the open, but they have a mobile phone, right? And the interesting thing is not that they have a mobile phone, it's that they have the infrastructure to charge that mobile phone. Right? And so people have come into these communities and they have put in place infrastructure that allows them to charge. And they are not government people, right? They are private sector who see an opportunity. And I think what the government needs to do is to try and do something very similar with water, because we have a lot of poor people that still don't have access to services. And so what the government should be trying to do is to set the standards, set what the expectations are, set, the public health protection regulations, and then allow different people to come into the market to try and provide services, because there are a lot of people that still don't have access, and it's criminal, right? And we have to find other ways of trying to meet the demands of those people. So I feel, again, a hybrid approach is what's needed. The government cannot legislate and decide on the types of technology that a wealthy family have to have and say that that's the same technology that a poor family needs to have. It's just not going to happen. And so there has to be some sort of flexibility in that type of thinking.
Yeah, since we also talk about decentralized systems, is there any thumb rule that dictates the size, in what place that needs to be used, how it would be adopted to the already existing system?
I think it's very context specific. I mean, there was a lot of work done some time ago where we felt, when you have decentralized systems, you want them to be as small as possible, but as large as they need to be. The largest they need to be is really about protecting public health, and so that they can be managed professionally. And so a lot of analysis that we did, 10 years ago, it was showing that decentralized systems, when they're serving populations of around 30 to 50,000 people, that's like a sweet spot, right? That's like a sweet spot where they can be managed professionally, but they also have all these benefits of reusing things close to source. That's just a rule of thumb, but it's very context specific.
One other specific questions from a sub-Saharan African continent. If there is a water scarcity, salient point there, how better can they manage their water resources, since there is a crucial lack of water and wastewater management infrastructure? And looking at the important deployment of carbon removal technologies, how do you see that affecting water resources? And also, since our direct air capture have possibility to extract water from atmosphere. So what is your thought on those two questions?
I didn't fully get the question, but what I would say is that where there is water scarcity, I think the key, as I said earlier, is to really think about the productive use of water, right? What is it you want the water to do for you? And how can you match the quantity and the quality of water to that intended purpose? And if you start thinking like that, you start to look at how you can reuse water multiple times. And if you already start saying, I'm going to reuse my water, where you place your treatment systems, where you place your industry, where you place things become very relevant, because you want everyone to be part of a system where you can cascade the use of water. So the only way I see us managing, in a time where the water availability becomes much less, is to try and think about how different water users can sort of provide positive reinforcements of each other. So if you take India, for example, right, the ag sector uses a lot of water. And the ag sector should be best cousins with the urban sector, because the urban sector, a lot of the water that they use and the wastewater that they generate can be productively used by the ag sector. So if you have these two sectors talking to each other and realizing the synergies that exist, then you can reduce your overall water footprint. In Chennai, industry is using a lot of reused water, right? So you're able to sustain the industry without increasing your overall water footprint. So this idea of creating sort of an ecosystem where all the different users of water are supporting each other and reinforcing each other by using their resources multiple times, I think is critical. And for that, the only way to do it is through systems thinking. It's to understand that water is a system of systems, right? And only when you do that will you see these positive reinforcements taking place.
And a couple of personal questions from me, since I am also the chair for IWP India. Yeah. So how do you see the potential of young water professions across the globe? And what is your narrative on where do you see them in future directions in taking actions as well as in policy decisions?
Look, right, our generation, my generation, my father's generation, we built things at a time where, the world was very different. We thought, populations would remain relatively small. we thought the environment was benign, and we thought our resources were endless, right? And so we built infrastructure systems which are really not fit for purpose in the current climate. Now, unfortunately, the young are inheriting these systems, right? But it's going to be the young that are really going to make the difference, right? Because they are thinking more out of the box. They're more imaginative, right? They're using more of their right brain. And I think that the future is really in their hands. And I think that it's going to be the young water professionals who really get us out of the mess that we see ourselves in the water sector. And I see this every day within IWA because I engage with young water professionals. And when I listen, and some of what I'm presenting is coming from those discussions with young water professionals, when I listen to their ideas, when I listen about how they're going to leverage, say, digital innovation to help make better decisions moving forward, when they recognize that from the outset we have to think about using water multiple times, having a closed loop, right? They are approaching things very differently. And so the young water professionals are the future of our sector, and they are the future of the world. And so I have a lot of confidence in those young water professionals, and I think that their level of understanding of the challenges we face and their level of understanding of the solutions that are out there to help us make those changes are there. And I think it's for us, the older generation, to give them space, give them confidence, and give them the opportunity to make that difference and not try to stifle them too much, because that is a problem I also see. But I'm very confident that the young are going to be the ones that are going to be the champions of the change that we desperately need.
Yeah. And in the world now, we are seeing data as a very potential goal. So having many data centers across the globe, and it requires a lot of water as it is cooling. So what is your take on that? Like we have many data centers because we need a lot of data to understand the system and to have a very good framework. And likewise, as we also know that there is a water crisis. So then how do you balance these two things?
Yeah, this is really a difficult sort of, it's a paradox, right, in a way. And within IWA, we're just starting a new initiative to look at these challenges, right, that we have. I mean, we all want to use what's coming out of these data centers, but equally, these data centers are crippling certain areas, right, because they're just sucking up all of the resources, both energy and water, in certain localities. And so it is a very, very complicated issue to deal with. Now, in Glasgow at our World Water Congress, we will have a couple of workshops focusing on this, and we have people, we've commissioned a group of people to provide us with a better understanding. Now, as I speak, what I'm learning is that these data centers are becoming much, much more efficient in the way in which they're using water. I don't know if that's true, but this is what I'm hearing. And I'm hearing that the new generation of data centers will, be much more responsible in the way that they use water for cooling. But as I said, it's work in progress. It's still a new area, right? And so I don't want to say anything without having the data in front of me, but it is an area that IWA will be presenting some findings. And I have a meeting later this afternoon with someone from Switzerland who's doing some of the work for us. So we are looking at this, but I think it's still an area that's evolving, right? So I can't really comment too much. It's going to put major challenges on us, and there's going to be other twists in the road, right? That happen every time some innovation appears. It's going to have some impact. But I think that we always find a way out of this. I mean, the current trajectory is clearly not sustainable with these data centers. But anyway.
Professor Kala? Yeah, thank you. And back to you, Ms. Polinius. So over to you.
Thank you, Danish.
Yeah, thank you as well from my point of view and in the name of DAAD. It has been a very insightful lecture on a very, very important topic. So yeah, once again, thank you. The lecture will be shared online on YouTube in some days. Thank you, Danish, for moderating the session, and as well to Edel Günther. Yeah, the audience, if you would like to join again, we have 3 more sessions this year. I think my colleague will now share as well whom sessions we're talking about. So there will be one lecture in July from the Ministry of Environment and Sustainable Development of Colombia. So Irene Vélez-Torres will speak about transitioning away from fossil fuels and scientific and political perspectives. She organized the recent conference in Santa Marta on fossil fuel exit. And so I think this is the next important topic, and we hope to see many of you there again. Thank you and goodbye. Have a good day.
Bye, everyone. Bye. Thank you.